One of the most important things you need to understand in order to write Plutus smart contracts is the counting model that Cardano uses. And that is the so-called E-UTXO model, which is an abbreviation for Extended Unspent Transaction Output Model. The UTXO model, without being extended, is the one that has been introduced by Bitcoin. But there are other models. Ethereum, for example, uses a so-called account-based model, which is what you're used to from a normal bank, where everybody has an account and each account has a balance. And if you transfer money from one account to another, then the balances get updated accordingly. But that is not how the UTXO model works. Unspent transaction outputs are exactly what the name says. They are transaction outputs, that is outputs from previous transactions that happened on the blockchain that have not yet been spent. So let's look at an example where we have two such UTXOs. One belonging to Alice, 100 ADA, and another one belonging to Bob, 50 ADA. And as an example, let's assume that Alice wants to send 10 ADA to Bob. So she creates a transaction. And a transaction is something that has inputs and outputs. Can be an arbitrary number of inputs and an arbitrary number of outputs. And an important thing is that you can always only use complete UTXOs as input. So if she wants to send 10 ADA to Bob, she can't simply split her existing 100 ADA into a 90 and a 10 piece. She has to use the full 100 ADA as input. So by using the UTXO of 100 ADA as input to a transaction, Alice has now spent that UTXO. So it's no longer a UTXO, it's no longer unspent, it's been spent. And now she can create outputs for a transaction. So she wants to pay 10 ADA to Bob. So one output will be 10 ADA to Bob. And then she wants her change back. So she creates a second output of 90 ADA to herself. And so this is how, even though you always have to consume complete UTXOs, you can get your change back. So you consume the complete UTXO, but then you create an output for the change. And note that in a transaction, the sum of the input values must equal the sum of the output values. So in this case, 100 ADA go in and 10 plus 90 ADA go out. This is strictly speaking not true. There are two exceptions. The first exception is transaction fees. So in the real blockchain, for each transaction, you have to pay fees. So that means that the sum of input values has to be slightly higher than the sum of output values to accommodate for the fees. And the second exception is the native tokens that we have on Cardano. So it's possible for transactions to create new tokens, in which case the outputs will be higher than the inputs, or to burn tokens, in which case the inputs will be higher than the outputs. But that is a somewhat advanced topic, how to handle minting and burning of native tokens in Plutus, and we'll come back to that later in the course. So for now, we'll only look at transactions where the sum of the input values equals the sum of the output values. So this is a first example of a simple transaction, and we see that the effect of a transaction is to consume unspent transaction output and to produce new ones. So in this example, one UTXO has been consumed, Alice original 100 ADA UTXO, and two new ones have been created. One 90 ADA UTXO belonging to Alice and another 10 ADA UTXO belonging to Bob. It's important to note that this is the only thing that happens on a UTXO blockchain. The only thing that happens when a new transaction is added to the blockchain is that some former UTXOs become spent and new UTXOs appear. So in particular, nothing is ever changed. No value or any other data associated with a transaction output is ever changed. The only thing that changes by a new transaction is that some of the formerly unspent transaction outputs disappear and others are created. But The outputs themselves never change. The only thing that changes is whether they are unspent or not. Let's do one other example, a slightly more complicated one, where Alice and Bob together want to pay 55 ADA each to Charlie. So they create a transaction together, and as input, Alice has no choice. She only has one UTXO, so she uses that one. And Bob also doesn't have a choice because neither of his two UTXOs is large enough to cover 55 ADA. So Bob has to use both his UTXOs as input. This time we need three outputs. One, the 55 plus 55 equals 110 ADA for Charlie, and then two change outputs. One for Alice's change and one for Bob's change. So Alice paid 90, so she should get 35 change, and Bob paid 60, so he should get 5 change. One thing I haven't yet explained is under which conditions a transaction can spend a given UTXO. Obviously, it wouldn't be a good idea if any transaction could spend arbitrary UTXOs. If that was the case, then Bob could spend Alice's money without her consent. So the way it works is by adding signatures to transactions. So for our first example, our transaction 1, because that consumes an UTXO belonging to Alice as input, Alice's signature has to be added to the transaction. And in the second example, because there are inputs belonging to both Alice and Bob, both Alice and Bob have to sign that transaction, which incidentally is something you can't do in Daedalus. So you would have to use the Cardano CLI for complex transactions like that. Everything I've explained so far is just about the EUTxO model, not the extended EUTxO model. So this is all just a simple EUTxO model. And the extended part comes in when we talk about smart contracts. So in order to understand that, let's just concentrate on one consumption of a UTXO by an input. And as I just explained, the validation that decides whether the transaction that this input belongs to is allowed to consume that UTXO in the simple UTXO model relies on digital signatures. So in this case, Alice has to sign the transaction for this consumption of the UTXO to be valid. And now the idea of the extended UTXO model is to make this more general. So instead of just having one condition, namely that the appropriate signature is present in the transaction, we replace this by arbitrary logic. And this is where Plutus comes in. So instead of just having an address that corresponds to a public key and that can be verified by a signature that is added to the transaction, instead we have more general addresses that are not based on public keys or the hashes of public keys, but instead contain arbitrary logic that can decide under which condition this specific UTXO can be spent by a transaction. So instead of an address going to a public key, like Alice's public key in this example, there will be an arbitrary script, a script containing arbitrary logic. And instead of the signature in the transaction, the input will justify that it is allowed to consume this output with some arbitrary piece of data that we call the redeemer. So we replace the public key address, Alice in our example, by a script, and we replace the digital signature by a redeemer, which is an arbitrary piece of data. Now the next question is, what exactly does that mean? What do we mean by arbitrary logic? And in particular, it's important to consider what information, what context the script has. So there are several options. And the one indicated in this diagram is that all the script sees is the redeemer. So all the information the script has in order to decide whether it's okay for the transaction to consume this UTXO or not is looking at the redeemer. And that is the the thing that Bitcoin incidentally does. So in Bitcoin, there are smart contracts. They are just not very smart. They are called Bitcoin script. And Bitcoin script works exactly like this. So there's a script on the EUTxO side and a redeemer on the input side. And the script gets the redeemer and can use the redeemer to decide whether it's okay to consume the EUTxO or not. But that's not the only option. We can decide to give more information to the script. So Ethereum uses a different concept. In Ethereum, the script basically can see everything, the whole blockchain, the whole state of the blockchain. So that's like the opposite extreme of Bitcoin. Bitcoin, the script has very little context. All it can see is the redeemer. In Ethereum, the scripts, the Solidity scripts in Ethereum can see the complete state of the blockchain. So that enables Ethereum scripts to be much more powerful. So they can do basically everything. But it also comes with problems. Because the scripts are so powerful, it's also very difficult to predict what a given script will do. And that opens the door to all sorts of security issues and dangers, because it's very hard to predict for the developers of an Ethereum smart contract what can possibly happen, because there are so many possibilities. So what Cardano does is something in the middle. So it doesn't offer such a restricted view as Bitcoin, but also not such a global view as Ethereum, but instead chooses a middle way. So the script can't see the whole blockchain, can't see the state of the whole blockchain, but it can see the whole transaction that is being validated. So in contrast to Bitcoin, it can't just see this one input, the redeemer of this one input, but it can see that and all the other inputs of the transaction and also all the outputs of the transaction and the transaction itself. And the Plutus script can use that information to decide whether it's okay to consume this output. Now in this example, there's only one input, but if this transaction had more than one input, then the script would be able to see those as well. There's one last ingredient that Plutus scripts need in order to be as powerful, as expressive as Ethereum scripts, and that is a so-called datum, which is a piece of data that can be associated with a UTXO in addition to the value. So at a script address, like in this example, in addition to this 100 ADA value, there can be an arbitrary piece of data attached, which we call datum. And with this, we can actually mathematically prove that Plutus is at least as powerful as Ethereum. So everything, every logic you can express in Ethereum, you can also express in this extended UTXO model that Cardano uses. But it has a lot of important advantages in comparison to the Ethereum model. So for example, in Plutus, it is possible to check whether a transaction will validate in your wallet before you ever send it to the chain. So something can still go wrong. So for example, your transaction can consume an output, and then when it gets to the chain, somebody else has already consumed that output. This output has already been consumed by another transaction. You can't prevent that. But in that case, your transaction will simply fail without you having to pay any fees. But if all the inputs are still there that your transaction expects, then you can be sure that the transaction will be validated and that it will have the effect that you predicted when you ran it in your wallet. And this is definitely not the case in Ethereum. In Ethereum, in the time between you constructing a transaction and it being incorporated into the blockchain, a lot of stuff can happen concurrently, and that's unpredictable. And that can have unpredictable effects on what will happen when your script eventually executes. So that means in Ethereum, it's always possible that you have to pay gas fees for a transaction, although the transaction eventually fails with an error. And that is guaranteed not to happen in Cardano. In addition to that, it's also easier to analyze a Plutus script and to check or even prove that it is secure, because you don't have to consider the whole state of the blockchain, which is unknowable. You can concentrate on this context that just consists of the spending transaction. So you have a much more limited scope, and that makes it much easier to understand what a script is actually doing and what can possibly happen or what could possibly go wrong. So this is it. That's the extended UTXO model that Plutus uses. So to recapitulate, in extending the normal UTXO model, we replace public key addresses from the normal UTXO model with scripts, Plutus scripts, and instead of legitimizing the consumption of UTXO by digital signatures, as in the simple UTXO model, arbitrary data, that's called redeemer, is used on the input side. And we also add arbitrary custom data on the output side. And the script, as context, when it runs, sees the spending transaction, the transaction 1 in this example. So given the redeemer and the datum and the transaction with its other inputs and outputs, the script can run arbitrary logic to decide whether it's okay for this transaction to consume the output or not. And that is how Plutus works. One thing I should still explain is how datum, script, and redeemer are provided by the two involved transactions. The producing transaction that produces a script output and the consuming transaction that tries to spend such a script output as an input. Let's start with the datum. As I explained before, the datum is part of the output, so it's the responsibility of the producing transaction to supply it. However, even though that is conceptually correct, technically it's a bit more complicated, and there are actually three options to do this. So the first option is that the output only contains the hash of the datum, not the datum itself, but just its hash. And then the consuming transaction, if it wants to spend this script output, has to contain the actual datum. This first option is actually the cheapest option for the producing transaction because the hash is quite small, so the transaction is smaller because it doesn't contain the actual datum value. However, it makes it difficult to consume such a script output because somehow the creator of the consuming transaction must know the actual value of the datum, which in this case is not saved on the blockchain. The second option is that the output again just contains the hash of the datum, but the transaction itself in its body contains the full datum value. This makes that transaction bigger and hence a bit more expensive, but it also puts the actual datum value onto the blockchain so that other parties can look it up and then potentially spend this UTXO. However, it's not completely convenient because the Cardano node only sees this datum value during validation, but then forgets its value. So for somebody else to later discover the value on the blockchain, another tool is needed, something like a chain indexer or DB-Sync. When Plutus first came out in the so-called Alonso era, these two options were the only two available options. But since the Vasil hard fork, there's a third option. So in this third option, the output itself contains the datum. In this case, it's called inline datum. And it doesn't have to be repeated in the body of the producing transaction. And in that case, the consumer, the transaction that wants to spend this output, does not need to provide the datum. So in this case, the consuming transaction can be smaller and hence cheaper. So particularly from the point of view of a potential consumer, this third option is by far the most convenient. In this case, no additional tool is needed. The Cardano node or the Cardano CLI can give the value of such inline datums. In this course, we will mostly use the third option because, as I said, it's most convenient. However, for dApps in production, there may be reasons to prefer one of the first two options. Before we can talk about how scripts are provided to the blockchain, let's briefly look at Cardano addresses. So Cardano address has two parts, a payment part that's always present and an optional staking part. So the payment part is responsible for deciding under which conditions a UTXO sitting at such an address can be spent. So there are two options for the payment part. It can either be given by a pub key hash, the hash of a public key, or by a script hash, the hash of a Plutus script. If it's the first case, the pub key hash, then such a UTXO can only be spent by transactions that have been signed by the corresponding private key. If, on the other hand, it's given by a script hash, then the corresponding script is executed during validation. So whereas the payment part of an address decides about who has the right to spend a UTXO, the optional staking part of an address decides about who is entitled to the staking rewards and who is in control of delegation. And again, for the staking part, there are two options. It can be a pub key hash or a script hash. If it's a pub key hash, then the owner of the corresponding secret key is entitled to the rewards. If it's a script hash, then the corresponding Plutus script is executed for transactions involving staking. So for example, if a transaction tries to withdraw staking rewards and the staking part is given by a script, then the corresponding script will be executed during validation of such a transaction. In this course, we will mostly concentrate on the payment aspect. So most of the scripts we will look at will be used as validators, which are relevant for the payment part. But we will also see examples how Plutus can be used in staking related questions later. So when a transaction wants to produce an output locked by a script, it will send that output to an address whose payment part is the hash of that script. However, if somebody wants to consume such an output, the Cardano node needs to validate. And in order to validate, it needs to know the actual script in order to execute and run it and see whether validation succeeds. And there are two ways for this to happen. The traditional way, the only possible way before the Vasil hard fork, was for the consuming transaction to contain the script. Now, some scripts are used over and over again, hundreds or maybe even thousands of times. So in the past, the same script was included in a lot of transactions. So that was a lot of redundant data that was repeated over and over again. To address this issue, there's now, since the Vasil hard fork, another way, so-called reference scripts. I told you before that a UTXO can carry value and, in the case of a script UTXO, some datum. Since Vasil, it can optionally also carry a script. So when I create a UTXO, I can optionally attach an arbitrary script to it. And once that UTXO is on the blockchain, other transactions in the future, when they want to unlock a UTXO locked by this script, can reference the script. So instead of including the script in the transaction, they can just say, I want to use the script sitting at that UTXO, which makes such consuming transactions much smaller and avoids the redundancy of repeating the same script over and over again. In both cases, whether the script is included in the transaction or referenced, the Cardano node will of course make sure that it is the right script. Right in the sense that when you hash it, you get the right hash value given by the payment part of the address. Finally, the redeemer is always supplied by the consuming transaction. It has to be, because the producing transaction has no idea what redeemer will actually be used. That's solely the responsibility of the consuming transaction. So whenever a transaction wants to consume a script output, it has to include the redeemer in the corresponding input. So this is the EUTxO model, the extended unspent transaction output model. And that is, of course, not tied to a specific programming language. I mean, what we have is Plutus, which is based on Haskell. But in principle, you could use the same concept, the same E-UTXO model with a completely different programming language. Actually, there are other blockchains also using the EUTXO model, but not using Plutus, the Ergo blockchain, for example. Cardano, however, uses Plutus, or to be more precise, Plutus script, which you can think of as the assembly language of the Cardano blockchain. The normal way to create Plutus script is via so-called Plutus TX, which is basically Haskell. And that's the method we will use in this course. So we write Haskell programs that get then compiled to Plutus script. There are alternatives, however, and we will briefly look at some of those in the last lecture of this course.